Good morning. So today we start with a new topic. I remind you that the topics, the multivariate statistical techniques that are included in the program of this course are mainly five. The basic matrix algebra, cluster analysis, multiple linear regression analysis, factor analysis and principal component analysis, and finally composite indicators. The topics, the first three topics, so basic algebra is a sort of introduction to useful for all the other topics related to statistical techniques. Cluster analysis and multiple linear regression analysis presented by Professor Mini concern mainly statistical techniques for classification of statistical units and for prediction. So mainly cluster analysis is a method for classification, and multiple linear regression analysis is a method for prediction. The other two topics, factor analysis and principal component analysis, and composite indicators, concern mainly dimensionality reduction, in the sense of summing up the information of the whole data set by reducing the number of variables. So we start from an original data set with a given number, usually a high number of response variables, and we try to reduce, to simplify the data set from the point of view of the number of variables, finding out which variables are unuseful, or at least less useful, because they don't provide new information with respect to other variables in the data set. So we try to reduce the number of variables with a final goal of keeping most of the original information provided by all the variables of the data set. So we can say that if we compare cluster analysis with factor and principal component analysis and composite indicators, the new techniques that we are going to discuss from today and in the remaining part of the course, we can say that cluster analysis is oriented to statistical units. The goal of cluster analysis is to simplify the data set from the point of view of the statistical units. So the goal, you know, is to group the units into homogeneous clusters, homogeneous groups, on the opposite, factor analysis and principal component analysis, but also the techniques related to composite indicators, have a similar goal, but variable oriented. So they try to simplify the data set from the point of view of the variables and not from the point of view of units. They are considered just one topic, factor analysis and principal component analysis, because they are similar techniques. There is an approach within the techniques used for factor analysis. The most commonly used is very similar to principal component analysis, and usually if you apply this very typical approach of factor analysis, you can get the same results that you can obtain with the application of principal component analysis. Anyway, let's focus on these specific techniques. we did some exercises, typical exercises of the exam concerning cluster analysis and basic matrix algebra and multiple linear regression analysis. After the presentation of these new topics, we will do exercises about these new topics too, and exercises with the use of software R. So we will see how to apply these techniques with the software R, and we will do typical exercises of the written exam concerning these techniques, as we did with cluster analysis, basic matrix algebra, and multiple linear regression analysis. Anyway, today we will continue from the point of view of the software. We will conclude the part concerning exercises about cluster analysis, and from the next lecture we will start doing exercises about that consist in the application of factor and principal component analysis with R. Anyway, so let's start talking about factor analysis and principal component analysis. So first of all, factor analysis is a multivariate technique. So let's see some basic notions. So factor analysis, we can briefly indicate it like that. FA, factor analysis, is a multivariate technique you know that multivariate techniques are techniques applied to multivariate data sets where we have more than one variable, and so they take into account complex data sets from the point of view of the number of variables, and so this is why factor analysis is a multivariate technique. For the analysis of data structure, of course singular, so technique, not techniques, just one. A multivariate technique for the analysis of data structure. So the main goal of factor analysis is to analyze the data structure, and we can say, as previously said in the introduction, to simplify the data set from the point of view of the number of variables. In other words, from the point of view of the number of columns of the data set. This is why we speak of data structure, because usually factor analysis is not the final analysis of our statistical study, but usually factor analysis is a sort of preliminary analysis useful for the application of other statistical analysis, just to simplify a complex data set from the point of view of the number of variables. What's the final goal of factor analysis? The goal of factor analysis is to reduce the number of informative variables so the number of columns of the data set through the definition of new variables called factors. This is why the technique is called factor analysis, because the final output of a factor analysis is the creation of new variables, new response variables that replace the original ones, the observed ones, and these new variables are called factors. So we start with a given number of observed variables, and the final output consists in new variables called factors. The number of new variables, the number of factors is possibly much lower than the number of original variables. But of course the main idea is to reduce the number of variables, but we must try to not lose much of the original information provided by the original observed variables, because the idea is simplification of the data set from the point of view of the number of variables, but not to lose the original information provided by the original variables. So how to reach this goal with factor analysis? Mainly, so the method that is applied is considered in order to reach this final goal. The method is a transformation of the structure of observed data a transformation of the original matrix of the original data frame with the variables under study from the matrix algebra point of view into a new structure, in other words, into a new matrix, a new data frame. Such that the data variability is explained by the factor. The factors are the new variables, so the output of factor analysis. In other words, the columns of the new data set, the columns of the new matrix, and when I told you that the factors have to keep the original information provided by the observed original variables, I mean that the factors must explain the original variability of data, because basically when I speak of information, I mean variability. So statistically speaking, information is variability. I will deepen this concept later, but this is a central aspect, a core aspect of this analysis, a core concept. So I want it is very clear, because it's the most important starting point of the factor analysis and principal component analysis. Imagine, for example, the data concerning the Passito survey. I know that Professor Mini introduced and presented this experiment, the experiment about the wine called Passito, where 386 persons, wine drinkers, were interviewed. So a questionnaire was given to these 386 people in order to understand, in order to collect data about or information, if you prefer, about their preferences and behaviors concerning drinking wine and drinking Passito wine specifically. It's a marketing study, a marketing survey. From the point of view of factor analysis and principal component analysis, since in this questionnaire is made of several questions concerning habits and behaviors of these persons about wine and about Passito wine in particular, the idea is, since we have too many variables, maybe we can simplify the data set and we can sum up the information about habits and behaviors and preferences of these people about wine in general and Passito wine specifically, finding out new variables called factors, and these new variables represent habits, behaviors and preferences of these persons about wine, but the number of new factors is lower, possibly much lower than the original variables that correspond to the original questions of the survey. For example, you know that among the questions there were questions like how much do you like drinking wine? All these questions were associated to numeric answers, where the answers in a scale from 1 to 7 or from 1 to 5 represent, or in one case from 1 to 4, they represent the level of liking, for example, or the frequency of some habits and behaviors, or the level of knowledge about some aspects and so on. So they sum up, they represent, we can say, the attitudes of these people with respect to wine and Passito wine specifically. Some examples of questions: how much do you like drinking wine? How often do you drink wine at home with meals? How often do you drink wine in bars or pubs? How often do you drink wine at restaurants with meals? Do you know the wine Passito? How often do you drink Passito? How much wine do you drink in 1 year? How much do you like drinking Passito? How much do you like aroma and smell of Passito, and so on. So several questions. Let me count. If I'm not wrong, 17 different questions, so 17 different variables concerning habits, behavior and preferences of persons about wine and Passito wine specifically. So too many. So maybe we can sum up the information and reduce the number of variables in order to simplify the analysis of habits, behaviors and preferences of these persons. All of them are numeric. There are factor analysis techniques for categorical variables, but in this course we will consider only factor analysis applied to numeric variables, and all the examples considered will be related to this case, multivariate data set with numerical variables. So what's the the properties of the factors. The factors, the final variables that represent the final output of factor analysis, they must have specific properties in order to be consistent with the idea of keeping the original information about the data, the original information provided by the original observed variables, and the idea that each factor provide different information with respect to other factors, because the summary of the original information is effective if each factor represent different information with respect to the other factors. So factor properties mainly are: they are uncorrelated with each other, and this is very important and a very important property, because this the incorrelation between factors implies that each factor provide different information with respect to other factors. I will deepen this concept, but you know that when two variables are correlated, then it means that we can predict the values of one of these variables as a function of the values of the other variable. So we can use a linear model, a linear equation, the equation of a straight line, in order to predict the values of one variable as a function of the other. And it means that basically if we know the values taken by one variable, we can predict the values of the other one. So we don't need the observation of both the variables, because the values of one of the two can be predicted when we know the values of the other. So the higher the correlation between two variables, in this case two factors, the higher the possibility to predict the values of one variable as a function of the other with a linear model. So this is why we need the factors to be uncorrelated, because the new variables, the factors, must provide different information, new information with respect to the other factors. So uncorrelated with each other. I will deepen this first property, because this is really a central concept in the factor analysis and principal component analysis. Second property of the factors is that they represent unobserved latent variables. Unobserved latent variables which reproduce the existing correlations between original variables, which reproduce the existing correlations between original variables. So they are unobserved latent variables. I want to deepen this concept because giving you a typical example, a typical framework where factor analysis is applied, and I'm talking about psychology. Psychological concept like cleverness, for example. I'm thinking to the QI index, for example, IQ index, the intelligence quotient. It's not something that you can measure, so cleverness cannot be measured directly. There is not a tool, an instrument that you can use in order to directly measure the cleverness, but even the capacity of applying logic, for example, the capacity in logic, the verbal capacity of people, or something like that. There are some mental or psychological concepts that cannot be directly measured, but we can indirectly measure these concepts through to some questionnaires, to questionnaires that are used in order to collect some data concerning people, and according to the answers provided by the persons, provided by the interviewed people, we can understand something about these persons, about some psychological attitudes, about some psychological capacities that cannot be directly measured. So the new concepts, cleverness or capacity in logic or others, are indirectly observed because basically they are unobserved latent variables. In many cases, when we apply principal component analysis or factor analysis, we don't know how many or which latent variables can be obtained from a data set through the application of factor analysis or principal component analysis. But how many latent variables and which ones is one of the output of our method, one of the output of factor analysis. So this is why it is considered a data-driven method, because the final result depends on the observed data. So this is not a technique similar to test of hypothesis, for example. In the test of hypothesis, you know what you want to prove, you know what you are investigating, and you know what do you want to understand from your data. So what's the information that you are looking for? In this case, you don't know the final output. Another way to describe this aspect is that factor analysis and principal component analysis are considered explorative methods, because you don't know what will be the final result, the final output, but you just look into the data set in order to find a final output that is unobserved, and it depends on the observed data, and specifically in this case depends on the correlation between original variables. Why? Because if we need to sum up the information from the point of view of the variables, so we can say that we need to group some variables together. So this is a technique from this point of view similar to cluster analysis, but oriented to variables instead of being oriented to units. Of course, we can group similar variables, and with similar variables I mean variables that provide similar information. In other words, variables that are highly correlated for the reasons I told you before. So the factors are unobserved latent variables that are created according to the correlations between the original observed variables. Another aspect is that the final output of a factor analysis, and this is typical of explorative methods, typical also of cluster analysis, for example, another explorative method, is that you cannot you can get a different final output that satisfy the original conditions to which you have constrained your analysis. I mean, there are different possible ways to sum up the information provided by a given data set, provided by the original observed variables, finding new factors. The final performance, performance of the method in terms of capacity of summing up in a very effective way the original information, effective from the point of view of the final number of variables that must be low, but also in terms of capacity of keeping most of the original information of the original data set. We can have different possible solutions, different possible set of new variables, factors, that satisfy given properties in terms of number of new variables, possibly low, and quantity of information preserved with respect to the original information provided by the observed variables. Finally, another important property of factors is that the original variables are linear combination of factors, and this is a property, another very important property connected with the approach that will be followed in order to find these new factors. The idea is to link the new factors, so the new variables, to the original ones by means of equations, linear equations. In other words, the original variables are linear combinations of factors. Linear combinations of factors. So the starting point is a set of linear combinations of the factors in order to explain the original variables as function of the factors. And this is another important aspect that characterizes factor analysis. Factor analysis, as many other statistical techniques, almost all statistical techniques, are based on some assumptions. Let's see the main assumptions of factor analysis. So let's talk about factor analysis at the moment in particular. later we will talk about principal component analysis. Factor analysis can be applied to a set of numeric standardizable variables. Numeric standardizable variables. And this is the first important assumption. The number of statistical units, this is an important condition for the application of factor analysis. The number of statistical units must be at least 5 times the number of original variables. Original variables. So if these conditions are not satisfied, you cannot apply factor analysis. Anyway, these are quite mild conditions, not too complex, and the factor analysis can be applied to a set of numeric standardized variables. It means that we can apply factor analysis to numeric variables. I told you that there are similar techniques that can be used for categorical variables, but we are not dealing with these techniques, with these problems, and the numeric variables can be standardizable. So in order to standardize variables, you must compute the mean of this variable and the standard deviation and the variance. So basically, standardizable variables are variables such that the mean and the variance can be computed, or the means and the mean and the standard deviation. What about the second assumption? The second assumption is necessary in order to apply. It's a technical assumption. So if the number of units is at least 5 times the number of original variables, you can apply with success factor analysis. Otherwise, you cannot apply factor analysis. If you have 10 variables, for example, you must have at least 50 observations, so 50 statistical units in order to apply factor analysis. So you must remember these properties because they are conditions for the applicability of this technique. Now the starting point of factor analysis is the so-called factor model. The factor model is the starting point of this technique, and it is connected with one of the properties mentioned above. The fact that the original variables are linear combinations of factors, but also to other properties like the uncorrelation between variables. So let's consider that we have k observed response variables x1, x2, xk. So this is the factor model. x1, x2, xk are the observed original numeric variables, observed response variables. I underline observed because I told you that the new variables are not observed because they are latent variables. So x1, x2, xk are observed response variables. And these variables are characterized by these properties. So response variables such that so the expectation of xj of the jth variable is equal to mu j. So let's denote the mean value, the expectation of the jth variable with mu j. The variance of xj is denoted by sigma jj. I told you that the factor analysis can be applied to numeric standardizable variables, so the expectation and the variance of this of each of the observed response variables can be computed. The variance can be also denoted by sigma j squared, where sigma j is the standard deviation, and the covariance between each possible couple of response variables xj, xr, xj, xr is denoted by sigma jr, with j and r equal to 1, 2, up to k. So the equations mentioned above, the equations that represent the linear combinations that link the observed response variables to the factors are the following. So xj, the variable xj, the jth observed variable, is equal to lambda j1 times f1 plus lambda j2 times f2 times plus and so on, plus lambda js times fs and so on, plus etc., plus lambda jq times fq plus uj plus mu j. Briefly, we can write this as the sum with respect to s of lambda js times fs plus uj plus muj, and this is true for j equal to 1 to up to k. So these are the equations or linear combinations where each observed original variable xj is expressed as a function of the factors. The factors are these new latent variables represented, denoted with f1, f2 up to fq. So the number of new variables is q, and q must be possibly much lower than k. For sure q must be less than k, possibly much less than k. uj is a sort of error, so is the information about xj not explained by the factors uj. It takes a similar role of the error in the regression model, for example. The factors takes a similar role of the explanatory variables in regression analysis, and muj is not a variable, uj is a variable, f1, f2, fq are variables. Muj is not a variable, but it is a constant, and it represents the mean value or the expectation of the jth variable, of the jth observed variable, xj, response variable. The coefficients of the linear combination lambda j1, lambda j2, lambda js are the coefficients concerning the explanation of xj through the factors f1, f2, fq. These parameters are called factor loadings. So the parameters, so they are not variables, they are not constants, they are not so they are coefficients, they are parameters. Lambda j1, lambda j2, lambda jq with j equal to 1 to up to k. So these parameters are called factor loadings. Factor loadings. The factor loadings take a central role. They are very important in factor analysis. They represent one of the typical output of the factor analysis, and I will focus on this concept and on this objects, on this output of factor analysis. Basically, the factor loadings are the coefficients of the linear combination. So the factor loadings lambda j1, lambda j2, lambda jq are the coefficients of the linear combination, where the jth response variable xj is expressed as a linear combination of the factors f1, f2, fq. So the loadings are the coefficients concerning xj, the jth response variable. The new variables, so this is about the parameters. The new variables f1, f2, fq are called common factors or simply factors. Specifically common factors, of course they are random variables as the original variables, the response variables x1, x2, xk, at least in the starting model. This is the model, so this equation takes the same role of the regression model in regression analysis. So we are talking about random variables. After so the specification of the model is an important starting point, but after that we will process, we will analyze observed data, okay? But now we are talking about random variables. uj, the error, we can say the variable that takes the role of the error in the model, is called unique or specific factor. Because f1, f2, fq are the real factors of our model, the new variables that we have to find out that must replace the original response variables. They are called common factors because f1, f2, fq are included in all the equations. We have k different equations, one for each observed variable, k different equations like that. But f1, f2, fq, all the q factors, the q common factors are present in all these equations. This is why they are called common factors. All the response variables are explained as a function of these q factors, of these new q variables. Instead, uj is present only in the equation for xj. So each of these variables that represent the errors in the model, the errors in the equations, they are unique, one for each response variable. What we need is to focus on the factors f1, f2, fq, because the common factors are what we previously called factors. So the factors of factor analysis, the new variables that must explain the original information of the data set, are the common factors f1, fq, f1, f2, fq. So q is less than k, because k is the number of original variables, q is the number of common factors. Possibly q must be very much less than k. So with this symbol I mean that q must be so the greater the difference between k and q, the higher the effectiveness of factor analysis. So the effectiveness of the summary of the information through factor analysis, through the application of factor analysis. Of course, as all the summary, as all the synthesis of the information, the higher the synthesis, the higher the quantity of original information that we could lose. So we must pay attention to reduce the number of variables, so to find out a number q of common factors very much lower than k, less than k, but possibly we must try to keep most of the original information provided by the the k original response variables. Let's consider some assumptions about the model. Some assumptions about the factors. The factors must be centered, so the distribution of the common factors must be centered on 0. So the expectation of each factor, expectation of fs is equal to 0 for s equal to 1 to up to q. So all the factors must have a mean null, so equal to 0. The variance of each factor, the variance of fs, must be equal to 1. So s equal to 1 to up to q. So for every s, the variance of the factor fs must be equal to 1, and the covariance between fs and ft, a given couple of factors fs and ft, must be equal to 0. S and t equal to 1 to up to q, and s not equal to t. So in other words, the factors must be standardized variables, so variables with mean equal to 0 and variance equal to 1, and they must be uncorrelated, so the covariance and consequently the correlation between each possible couple of factors must be equal to 0. The fact that they must be standardized variables comes from the idea that we must consider the information that they can provide to the about the original data set, but the how can I say, the information must not be affected by the original unit of measurement of the variables. So this is why we need to standardize the original response variables, and we must consider the factors as standardized variables. Okay, so the standardization is important in order to avoid that the unit of measurement or the magnitude of the original variables can affect the final result, and is also important for the comparison between the different variables, because we could have k variables with expressed in different unit of measurements, and so in order to compare them and in order to comparability, yes, and as I said, to avoid that the unit of measurement can affect the final result, we need to standardize. So the factors, they must be standardized variables. The covariance equal to 0, so the uncorrelation between factors, as I said, is important because I need a new, in order to make the summary of the information very effective, I need to find out standardized, uncorrelated variables, because I want to avoid that the new variables provide similar information. Each factor must provide a different information with respect to all the other factors, and this statement is formally expressed as uncorrelation between the factors, so the covariance must be equal to 0. Other aspects of the variables of the model. So these properties characterize the factors. Other properties are that the unique factor must be also a variable with mean equal to 0. So the expectation of uj is equal to 0 with j equal to 1, 2, up to k. And the variance of uj must be equal to sigma uj. So I denote with a subscript on the left u in order to distinguish this is sigma jj, or also sigma uj squared. I use u as a subscript on the left in this case in order to distinguish the variance of the unique factor uj with respect to the variance of the original response variables sigma jj or sigma j squared, with j again equal to 1, 2, up to k. And the covariance between couples of unique factors uj, ur is equal to 0 with j and r equal to 1, 2, up to k, and j not equal to r. So if we consider any couple of unique factors uj, ur, these factors, these variables are uncorrelated too. So each unique factor provides a different information with respect to the others. So they are uncorrelated variables. Finally, so these properties concern the unique factors. Finally, the unique factors and common factors are uncorrelated. So the covariance between fs and the uj is equal to 0 with s equal to 1, 2, up to q, and j equal to 1, 2, up to k. So for any couple of common factors and unique factors, we have a covariance equal to 0, so null uncorrelation. In other words, all the factors are uncorrelated. Unique factors, common factors, and both of them, unique and common factors, all of them are uncorrelated. Okay, this is just a starting point, an introduction. In the next lecture we will go on with this preliminary information, and we will describe how to apply factor analysis and also principal component analysis. For the moment I think we can stop here, and we will continue next time. Later we will do exercises, we will complete exercises about cluster analysis with R, because we will start with exercises concerning factor analysis when we finish the preliminary part with the description, the theoretical introduction, and the description of this methodology started today. So see you later with exercises with R concerning cluster analysis.